Good day, CE Peeps! I am Jericho Kihaka from BSCE 3A and I will be discussing about the soil engineering for highway design. We all know for a fact that soils are extensively utilized in the construction of highways. That is why highway engineers are focused on the basic engineering properties of the soil. These properties are important to determine and analyze how highway will be able to withstand or carry loads and heavy traffic volume. Fundamentally, in highway construction, soil has to be strengthened for highway pavement. In this report, I will be presenting basic knowledge on soil engineering crucial for highway construction and design. To start with, we have the soil characteristics. One of the fundamental concepts in soil engineering is the understanding of the characteristics of the soil. Basically, the characteristic of the soil is described or can be described by different categories. This includes the origin, formation, grain size, and shape. Generally, the primary engineering properties of the soil is influenced or is related to the basic characteristic of that certain soil. Under the soil characteristics, we have the origin and formation of soil. Soil can be defined from civil engineering point of view as the loose mass of mineral and organic materials that cover the solid crust of granitic and basaltic rocks on the earth. To discuss further, the formation of the soil can be through weathering and other geological processes. Weathering being the commonly contributor in the formation of the soil is the result of physical and chemical actions, mostly the atmospheric factors changing the structure of the composition of the rocks. We can also classify soil as residual, meaning weathered materials are placed only above the original material by which they are formed. Or it can also be classified as transported, meaning the weathered materials are moved by water and wind as well as the glaciers and other agents away from the location of the original material. It can also be organic or inorganic depending on its composition. Soil can also be characterized through surface texture. The texture of the soil can be described in terms of its appearance depending primarily on the shape and size of the particles of the soil, as well as their distribution in the soil mass. It can be identified as fine textured soils consisted mainly of silts, clay, and from the name itself are small particle sizes. Another classification is the coarse textured soil, known to be consisted of sand and gravel, which is unlike the first classification, has bigger particles. Next, we have the basic engineering properties of soil. The basic engineering properties of soil is crucial for highway engineers to be familiarized with, since these influence the behavior of the soil when is subjected to external loads. Of these engineering properties, we have phase relations. We all know that soils are primarily constituted of various minerals of different sizes, and between them are spaces. The spaces, which is called as void, can be filled with air and or water. Therefore, the soil is considered to have three phase systems consisted of air, water, and solid materials. Under the phase relations, we have porosity, void ratio, moisture content, degree of saturation, density of soil, specific gravity of soil particles, and other relationships. We have to take note that the relative amount of voids in any soil is an important quantity that affects some aspects of soil behavior. This amount can be measured in terms of the porosity of the soil. The equation is defined as porosity is equal to the total volume of space occupied by air and water or the void over its total volume. Next, we have the void ratio. The amount of voids can also be measured in terms of void ratio as denoted by the equation void ratio is equated to the volume of the void over the volume of the solids. Next, we have the moisture content. From the word itself, moisture is the quantity of water in a soil mass which is defined by the equation moisture content is equal to the weight of water over the oven-dried weight of solids multiplied by 100. Take note that the moisture content is expressed in percent. Another one is the degree of saturation. It is described as the percentage of void space occupied by water. This is derived from the equation degree of saturation is equal to the volume of water over the volume of the void multiplied by 100. Next, we have the density of soil. It is one of the useful soil property that is essential to highway engineers. The density is the ratio that relates the mass side of the phase diagram to the volumetric side. There are three densities commonly used in soil engineering. First, we have the bulk density or the total density. Total density is equal to the ratio of the weight and the volume of the given sample, or is equated to oven-dried weight of soil plus weight of water all over the volume of the solid plus volume of water plus the volume of the air. We have to take note that the air is negligible. For saturated soil, the equation for total density is given as equal to the weight of the solid over the volume of the given sample, which is also equated to the oven-dried weight of solid plus weight of water all over the volume of solid plus volume of water. Second, we have the dry density. Dry density is equal to the oven-dried weight of solid over the volume of the sample, which is also equated to the weight of solid over volume of solid plus volume of water plus volume of air, which is also equal to the total density over 1 plus W. Third is the submerged density. Simply denoted as submerged density is equal to the saturated density minus the density of the water. We also have the specific gravity of soil particles. It is defined as the ratio of the density of the soil particles to the density of the distilled water. We can also derive other useful relationships presented previously with the basic definitions of phase relations. Another soil property that we have to understand is the Atterberg limits. Clay soils with very low moisture content will be in the form of solids. As the water content increases, however, the solid soil gradually becomes plastic. That is, the soil easily can be molded into different shapes without breaking up. The stiffness or consistency of the soil at any time, therefore, depends on the amount of the water present in the soil. From this, the Atterberg limits are the water content levels at which the soil changes from one state to the other. Under the Atterberg limits, we have the shrinkage limit, plastic limit, and liquid limit. First, we have the shrinkage limit. When a saturated soil is slowly dried, the volume shrinks but the soil continues to contain moisture. Continuous drying of the soil, however, will lead to a moisture content at which further drying will not result in additional shrinkage. The volume of the soil will stay constant and further drying will be accompanied by air entering the voids. The moisture content at which this occurs is the shrinkage limit or SL of the soil. Second, we have the plastic limit. Plastic limit or PL is defined as the moisture content at which the soil crumbles when it's rolled down to a diameter of 1/8 of an inch. The moisture content is higher than PL if the soil can be rolled down to a diameter of less than 1/8 of an inch, and the moisture content is lower than the PL if the soil crumbles before it can be rolled to 1/8 of an inch diameter. Third, we have the liquid limit. The liquid limit or LL is defined as the moisture content at which the soil will flow and close a groove at 1/2 inch within after the standard LL equipment has been dropped 25 times. We also have to take note that in determining the plasticity index, we have to find the difference between the liquid limit and the plasticity limit. We also have the liquidity index. As stated in the definition, liquidity index can be represented through the equation liquidity index is equal to the natural moisture content of the soil minus the plastic limit all over the plasticity index. We also have the permeability of the soil, which is defined as the property that describes how water flows through the soil and is given as the velocity of the water in the soil is equal to the coefficient of permeability multiplied by the hydraulic gradient. Lastly, we have the shear strength, which is important for highway engineers since soil masses will usually fail in shear under highway loads. It is denoted as shear strength is equal to the cohesion expressed in pound per square feet plus the normal stress on the shear plane expressed in pound per square feet multiplied by the tangent of the angle of internal fracture. Another topic under this report is the classification of soils for highway use. The systematic categorization of soil according to their probable engineering characteristics is a method defined as the soil classification. This is a process of identifying appropriate and suitable materials to be used on the subbase and examining the predicted probable behavior of the soil when used as subgrade material. It is an important step in highway engineering as the classification of soil becomes a great way of obtaining a general idea of how the soil will behave if used either as subgrade or subbase material. The American Association of State Highway Transportation Officials AASHTO Soil Classification System and the Unified Soil Classification System USCS are used in this process. First, let us discuss the AASHTO Soil Classification System. This classification system is a system described as a mean for determining the relative quality of soil for use in embankments, subgrades, subbases, and bases. Generally, the suitability of a soil deposit for use in highway construction can be summarized as follows. First, the soil classified as A1, A, A1B, A24, A25, and A3 are satisfactory to be used as subgrade and subbase material if it will or properly be drained. Also, this kind of soil should be properly compacted and covered with an adequate thickness of pavement. It is for the surface load to be carried. Second, materials that are identified as A26, A27, A4, A5, A6, A75, and A76 will require a layer of subbase material if used as subgrade. And if these are to be utilized as an embankment materials, there must be a special attention that must be given to the design of the embankment. And third, when soils are properly drained and compacted, their value as subgrade materials decreases as GI increases. The table presented shows AASHTO classification of soil and soil aggregate mixture. Another system for classification of soil is the Unified Soil Classification System, or the USCS. As a brief history of its origin, USCS originally was developed during World War II, and take note, not primarily for highway engineering but for airfield construction. It has been to series of modification in order to obtain the current version, which is also applicable to the types of construction such as for dams and foundations. The table shows the USCS definition of particle sizes. Another subpart of this topic is the soil surveys for highway construction. This is a fundamental key concept in soil engineering. When we say soil survey for highway construction, we are pertaining to the investigation, examination, and analysis of the characteristic of the soil, specifically as stated for highway route. We are to identify the most suitable soil for use as the sub-base and fill materials. It is a significant part for highway construction as it entails for the soil condition directly affects the location of the highway. In this matter, we have the geophysical methods of soil exploration through the two methods of soil exploration, namely resistivity method and seismic method. First, we have the resistivity method. Resistivity method is primarily based on the difference in electrical conductivity or resistivity of the different types of the soil. An electrical field is produced in the ground by means of two current electrodes. The resistivity equipment used is basically designed that the apparent resistivity can be read directly on the potentiometer. From this, the data for the soil profile are gathered by moving the electrode along the center line of the proposed highway, without changing the spacing. Another geophysical method for soil exploration is the seismic method. Seismic method is used to identify the location profiles or dense strata underlying softer materials. During this process, impact or shock waves are induced into the soil, and it can be by striking a plate located on the surface with a hammer, or could be through exploding small charges in the soil. The seismic test is being conducted through moving the shock-producing device along the proposed center line of the highway. The shock is produced at known distance from the geophone. Another subtopic of this report is the soil compaction. In soil engineering, or specifically for highway engineering, the process of compacting the soil remains a crucial stage. It is important that the material to be placed is uniformed and is compacted to a high density. Proper compaction of soil is observed in order to reduce the subsequent settlement and volume change to a minimum. With this, the strength of the embankment or subbase are enhanced and ensured. Under the soil compaction, we have the optimum moisture content. Optimum moisture content of any soil to be used as either an embankment or as a subgrade material is necessary to be determined first before doing any field of work. In today's manner, mostly are using the dynamic or impact test to determine the optimum moisture content as well as the maximum dry density. Next, we have the field compaction procedures and equipment. For field compaction procedures, we have to take note that the first step in the highway embankment is to identify and select the suitable material. It can be done through economically feasible barrow pits or barrow areas and testing them in the laboratory to be determined in terms of the group of each. Under the field compaction procedures, we have the embankment formation. The formation of highway embankments is done through spreading thin layers of uniform thickness of the material and compacting each layer at or near the optimum moisture content. It is not recommended to use the end dumping of materials from trucks. In this process, constructing one layer at a time is essentially made to achieve a uniform strength and moisture in the embankment. Next, we have the control of embankment construction. The construction of embankment control purposes deals with the frequent and regular checks primarily on the dry density and moisture content of the compacted materials. The measurement obtained in the field is directly the basis in obtaining the back density. Hence, the dry density is calculated from back density and moisture content. The test is conducted through two methods. Either of the two can be utilized. In the suction method, a cylindrical hole of about 4 inches in diameter and a depth of equal to that of the layer is excavated to determine the back density, while the non-destructive method involves the direct measurement of the in situ density and moisture content of the compacted soil. Unlike the destructive method, it utilized nuclear equipment. Next, we have the field compaction equipment. In field compaction, the equipment necessary or the compaction equipment itself are divided into two categories. These equipment are categorized as spreading equipment and compacting equipment. Spreading equipment include bulldozers and motor grader in spreading the materials to the required thickness. Meanwhile, compacting equipment include rollers and apply either a vibrating force or an impact force on the soil. Here are some of the equipment used in field compaction. We have the motor grader, smooth wheel roller, rubber tired roller, and sheep's foot roller. Most of this equipment are readily available in the market. The next subtopic we have is the special soil test for pavement design. There are still few tests used in undermining the strength or supporting value of a given soil, especially when they are used as a subgrade or sub-based material. Two of the most commonly used tests for soil testing, specialized only for certain categories, are the CBR test and beam stabilometer test. First, we have the California Bearing Ratio or the CBR test. This test involves to determine the load deformation curve of the soil in the laboratory using a standard CBR testing equipment. This test is done on sample of soil compacted to required standard and immersed in water for 4 days. During this stage, the samples are then loaded with such charge that simulate the estimated weight of pavement material soil will support. CBR is denoted to be equal to the unit load of 0.1 piston penetration test multiplied by pound per square inch over unit load of 0.1 piston penetration standard crushed rock multiplied by pound per square inch, or could also be CBR is equal to the unit load of 0.1 piston penetration in test sample over 1,000 multiplied by 100. Second, we have the beam stabilometer test. This test is generally used to determine the resistance value R of the soil to the horizontal pressure obtained by imposing a vertical stress of 160 pound per inch on a sample of the soil. The value of R is essentially to be used in identifying the thickness of the pavement above the soil. It is in order to carry the traffic load estimated. Under which are exudation pressure, which is defined as the comprehensive stress that will exude water from the compacted specimen. Next is the expansion pressure, which refers to indicate the load and therefore the thickness of the required material above the soil to prevent any swelling if the soil is inundated with water when used as a subgrade material. And lastly, the resistance value, which is referring to the schematic of beam stabilometer used in the phase of the test. Resistance value is equal to 100 minus 100 all over 2.5 over the number of turns of the displacement pump multiplied with the quantity of vertical pressure over horizontal pressure at PV minus 1 plus 1. The last subtopic we have is the frost action in soils. It is more likely that the decreasing temperature, even falling to freezing points for several days, water in the soil pores will get freeze, and that is something to be considered. There is a need to increase the volume of the soil, knowing that when water freezes, its volume obtains a 10% increment. Not just that, ice crystals that are high in terms of thickness may be formed in the soil. In this matter, we have to consider three conditions for frost action to occur. First, the ambient temperature must be lower than the freezing for several days. This condition is uncontrollable by humans, since this is a naturally occurring phenomenon. Therefore, it is more likely to occur on cold areas than in warm areas. Second, the shallow water table that provides capillary water to the frost line must be available. In this condition, there is a requirement for groundwater table to be within the height of the capillary rise. This will help the water be continuously fed to the growing ice lenses. And third is that the soil must be susceptible to frost action. This condition requires that the material or the soil should be of quality that is relatively high in terms of capillary pressures that can be developed, but at the same time that the flow of the water through its pores is restricted. To briefly sum up, in the design and construction of any highway, the selection of suitable soil to be used is primarily important. For highway engineers or transportation engineers, familiarizing soil properties and how will it be determined is a crucial task. I hope that you learned a lot in this presentation. Again, I am Jericho Dihakiaka, and that concludes my report.